Hello friends, continuing with the chapter electric potential and capacitance. Today we start with third topic of this chapter, electrical capacitance of a conductor. The first step required is the definition of electrical capacitance. I define ability of a conductor to store electric charge is defined as electrical capacitance of the conductor. I repeat, ability of a conductor to store electric charge is defined as electrical capacitance of the conductor. Mathematical expression. Let Q be the electric charge given to a conductor and it is raised to an electric potential V. As more and more charge is given to the conductor, its electrical potential is raised more and more. It is therefore electric charge and electric potential are in direct proportion with each other. That is, V is directly proportional to Q, or we can write Q is equal to CV. Let us mark it as equation 1, where C is constant of proportionality called as electrical capacitance of the conductor. If we plot VQ graph comes out to be as shown. V on perpendicular axis and Q on horizontal axis. Okay, so the VQ graph is a straight line. Now mathematical definition of electrical capacitance. From equation 1 we have C is equal to Q by V. Now because C is equal to Q by V, therefore electrical capacitance of conductor can be defined as the ratio of electric charge stored on the conductor and the electric potential to which it is raised. I repeat, the ratio of electric charge stored on the conductor and the electrical potential to which it is raised is defined as electrical capacitance of the conductor. Now fifth point, SI unit. The SI unit of electrical capacitance is farad. Now definition of farad. Because C is equal to Q by V and when Q is 1 coulomb, V is 1 volt, then C is equal to 1 coulomb by 1 volt and it is equal to 1 coulomb per volt or 1 farad. Thus, electrical capacitance of a conductor is said to be 1 farad when 1 coulomb of charge given to the conductor raises its electric potential to 1 volt. I repeat, thus electrical capacitance of a conductor is said to be 1 farad when 1 coulomb of charge given to a conductor raises its electric potential to 1 volt. Smaller units of capacitance. 1 farad equal to 10 raised to power 3 millifarad, or 1 millifarad is equal to 10 raised to power minus 3 farads. 1 farad is equal to 10 raised to power 6 microfarads, or 1 microfarad equal to 10 raised to power minus 6 farads. 1 farad equal to 10 raised to power 9 nanofarads, or 1 nanofarad equal to 10 raised to power minus 9 farads. 1 farad equal to 10 raised to power 12 picofarads, or 1 picofarad equal to 10 raised to power minus 12 farads. So you remember these conversion scales of microfarad, nanofarad and picofarad. Because capacitors which are practically available, they are of capacities microfarads, nicofarads and picofarads. Millifarads and farads values are not manufactured because of inconvenient sizes of these capacitors. So, since you are to use SI unit of capacitance as farad, so you must remember skillfully how to write 1 microfarad as farads and 1 picofarad as farads, or 1 picofarad as farads. So you are to use SI unit as farads, okay, in all cases. Now assignment 2.3, question number 1. Calculate electrical capacitance of a conducting spherical shell. Question number 2. Calculate electrical capacitance of earth. Take radius of earth equal to 6.4 into 10 raised to power 6 meters. Now the capacity may come out to be as 711 microfarad or so. You can calculate. Okay. Now drawbacks of a single conductor capacitor. Though a conductor has some electrical capacitance to store electric charge over it, yet the quantity it stores is very small. To overcome this difficulty, more than one conductors are arranged in order to obtain large capacitance, to store more charge, and that too in a small space. As shown in diagram, we have two conductors instead of one conductor for making a capacitor. This capacitor can store large amount of charge, that too in a small space. Now what is capacitor? Capacitor is a device to store electric charge, or a device to store electric charge is defined as capacitor or condenser. Sometimes we call it as condenser, which condenses electricity. So normally, technically, we call it as capacitor. It is an arrangement of two parallel conductors when one of the two conductors is connected to ground. The other conductor develops the ability to store large amount of electric charge over it. I repeat, a device to store electric charge is called as capacitor or condenser. It is an arrangement of two parallel conductors when one of two conductors is connected to ground. The other conductor develops the ability to store large amount of electric charge over it, and this device we call it as capacitor. Now, principle of parallel plate capacitor. Consider a single conductor A having charge Q and electric potential V, as shown in figure A. This charge stored being very small, its capacity is required to be increased. It can be done by bringing another conductor B near it, as shown in figure B. Now, due to electrostatic induction, conductor B becomes charged. Negative charge accumulates at inner surface and positive charge accumulates at outer surface. Negative charge tends to reduce electric potential of conductor A, and positive charge tends to increase electric potential of conductor A. Reduction is more than addition to electric potential of conductor A, because negative charge is more near to conductor A than the positive charge on outer surface of conductor B. Therefore, electric potential of conductor A reduces in order to bring electric potential of conductor A to previous value V, more charge, say dq, is required to be given to conductor A. Thus, capacity of conductor A to store charge increases. Further, capacity can be increased by grounding the outer surface of conductor B, as shown in figure C. Positive charge on outer surface of conductor B flows to the ground, and negative charge on inner surface cannot, being attracted by positive charge on conductor A. Now, additive effect due to positive charge on outer surface of conductor B disappears, and electric potential of conductor A reduces again. Now, in order to bring electric potential of conductor A to previous value V, more charge, say plus dq dash, is required to be given to conductor A. Thus, capacity of conductor A to store electric charge increases manifolds. This is how we can increase the capacity of a single conductor to store electric charge by bringing another conductor near it, where we can store in this arrangement of conductors, parallel conductors, more electric charge into, that is, two in small space. So, this is the explanation for the principle of parallel plate capacitor, or this constitutes the principle of parallel plate capacitor. Now, let us define capacitor. This arrangement of two parallel conductors, as shown in figure C, is called as parallel plate capacitor. Circuit symbol of capacitor is as shown in diagram. You mark it carefully. Now, classification of capacitors. Capacitors are classified on the basis of number 1, geometrical shape, number 2, dielectric substance used between the plates. So, let us take up one by one. First, we take up on the basis of geometrical shape. On the basis of geometrical shape, we come across number 1, parallel plate capacitor, number 2, spherical capacitors, number 3, cylindrical capacitors, and number 4, disc capacitors. And number 2, on the basis of dielectric substance used between the plates, we come across capacitor as number 1 as air capacitor. Air is used as dielectric. Number 2, paper capacitor, where paper is used as dielectric. Number 3, electrolytic capacitor, where electrolyte is used as dielectric. Number 4, polyester capacitor, where polyester is used as dielectric. Number 5, ceramic capacitors, where ceramics are used as dielectric substance between the plates of parallel plate capacitor. Okay. Now, charging of capacitor. Look at the diagram, circuit diagram. C is capacitor, R is resistance connected to capacitor and the central terminal of two-way key. K is one-way key, B is battery. Now, terminal 3 is connected to one plate of capacitor, C, and positive terminal of battery. Now, a capacitor can be charged by connecting 1 and 2 terminals as shown in diagram. When 1 and 2 are closed, capacitor gets charged through resistance R during time t equal to RC. T equal to RC being time constant of the circuit. I repeat, a capacitor can be charged by connecting terminals 1 and 2 as shown in diagram. When 1 and 2 are closed, capacitor gets charged through resistance R during time t equal to RC, being time constant of the circuit. Now, charge at any instant of time t is given by the equation Qt is equal to Q max into 1 minus e raised to power minus T by RC. I repeat, charge at any instant of time t is given by the equation Qt is equal to Q max into 1 minus e raised to power minus T by RC. Now Qt graph is a parabola. If you plot Q versus T graph, then the graph comes out to be a parabola. Now let us define time constant of the circuit. The time duration within which capacitor gets charged is defined as time constant of the circuit. It is given by the expression T equal to RC. It is given by the expression T equal to RC. Now another way of defining time constant is like this. The time duration within which capacitor retains 57% of the maximum value of the charge. I repeat, the time duration within which capacitor retains 57% of the maximum value of the charge is defined as the time constant of the circuit. So this is how we can charge a capacitor. Discharging a capacitor. A capacitor can be discharged through R by connecting 1 and 3 as shown in diagram. When 1 and 3 are closed, capacitor gets discharged through resistance R during time t equal to RC, being time constant of the circuit. I repeat, a capacitor can be discharged through R by connecting 1 and 3 as shown in diagram. When 1 and 3 are closed, capacitor gets discharged through resistance R during time t equal to RC, being time constant of the circuit. The charge at any instant of time t is given by the equation Qt is equal to Q max into e raised to power minus T by RC. If we plot the graph, again graph is a parabola. Q versus T graph is a parabolic graph. Now again we have to define time constant of the circuit during discharge. The time duration within which capacitor gets discharged, and it is given by the expression T equal to RC. Another way of defining time constant during discharge process, the time duration within which capacitor retains 43% of the maximum value of the charge. I repeat, the time duration within which capacitor retains 43% of the maximum value of the charge is defined as the time constant of the circuit. Okay. Now assignment 2.3 continued. Question number 3. What are the drawbacks of single conductor capacitor and how they are overcome? Question number 4. Explain the principle of parallel plate capacitor and give the equations of number 1 charging of a capacitor and number 2 discharging of a capacitor. Okay. So you try to answer these questions on the basis of the text that you have learnt. Thank you so much. God bless you.